That is your topic number 9, local electric field, E local. So let's start. So before we are going to start this topic in detail, I suggest to all of you that you just write down the short questions whatever we have been discussed in our last topic, which will be essential for your exam. Okay. So in this topic in detail we are going to discuss about local electric field. In short, it has been written as E subscript LOC, E local. Okay. So, so first of all, we are going to discuss overall idea about local electric field. Then we are going to evaluate mathematically local electric field. To do so, consider a dielectric material placed in between the parallel plate capacitor. Hence, whole dielectric material is going to be polarized. Okay, positive, negative, positive, negative. Due to which we can found EP, that is your depolarization electric field, which is induced due to the induced surface charge on the both the side of the dielectric material, and net electric field inside the dielectric material we can found E, which will be equal to E naught minus EP, where P is nothing but called as your polarization vector per unit volume inside the dielectric material. These things in detail we have been discussed in our previous topics. So to understand exactly what is called the local electric field, for that consider a cavity, this one, inside the dielectric material, and at the center of the cavity consider a atom or molecule. So see the center of this cavity, and at the center of the cavity we considered a atom or molecule, right? Now from the figure it can be found that this atom or molecule is influenced by this applied electric field E naught and depolarization field EP, and the charges which are induced on the surface of this cavity. See, this side, left side of this cavity is your positive charges, and right side we can found net negative charges on this cavity. So due to which we can get another electric field Es along this direction. So this atom also influenced by Es, which is nothing but called as your uh, electric field induced by the on the surface of this cavity, and also this atom or molecule can be influenced by the dipole moments, the permanent dipole moments present inside this dielectric material. Okay, suppose if we are going to consider this is a polar dielectric material, then before we have to apply the electric field inside this dielectric material also dipole moments are present. So due to the permanent dipole moments, we can expect another electric field, that is your EM. So here EM represents the electric field due to permanent dipole moment if this dielectric material is a polar. ES is the electric field intensity is due to surface charge on this cavity. EP is your depolarization field which is induced due to polarization of whole dielectric material or induced of surface charge on the two sides of the dielectric material, and E naught is your applied electric field. So here the atom or molecule which is at the center of this cavity is influenced by these four electric field intensities. E naught, that is your applied electric field, initial applied electric field. EP is your depolarization electric field which is induced due to polarization of dielectric material. Es is the electric field due to the induced charge on the surface of the cavity, this one, on the surface of the cavity, and Em is due to permanent, this Em electric field intensity due to permanent dipole moment present inside this cavity or surrounding of this molecule or atom which is at the center of this cavity. So here we consider that this dielectric material is a non-polar. So EM value will be 0. Okay. So net electric field intensity on this atom or molecule will be how much? This one, this much. Okay. So now we are going to calculate mathematically the value of E local. So whatever we have been discussed, in short, I have been written here. Here also I written that EM is the net electric field intensity at C due to presence of permanent electric dipole inside the cavity. That these things already we have been discussed. So from here you have to write down the note. Whatever we have been discussed in this slide, overall what I told, that overall idea about the local electric field, same thing from here you have to write. Okay. That means if this question asked for 6 mark in your exam, what you have to write? You have to start from here. From here, this is a simple definition of the local electric field, that the resultant electric field to polarize an individual atom or molecule inside a dielectric material is called local electric field. That means if we are going to consider a individual atom and molecule, this is your individual atom and molecule, then what is the polarization of this individual atom or molecule, that we have to calculate, or due to which electric field or what is the net electric field will be applied on this atom or molecule inside the dielectric material. So the simple definition is the resultant electric field to polarize an individual atom or molecule inside the dielectric material is called the E local. Okay. To calculate E local, consider an cavity of radius r. So this is the radius r. Okay, this is the radius r. I not written, you just write. Okay, this is the radius r. Having the center is at C, as shown in the figure 1. This is your figure 1, right? Now consider an atom or molecule placed at center C of the cavity. Then the resultant or local electric field, that is your ELOC, experienced by the atom or molecule will be how much? E local will be E naught plus EP plus ES plus EM, where E naught is your external applied electric field, EP is your depolarization field or field due to induced surface charges sigma p on the opposite faces of dielectric material, ES is the net electric field intensity at C due to surface charges on the cavity, this surface charges on the cavity, EM is the net electric field intensity at C due to presence of permanent electric dipoles inside the cavity. That means if we are going to consider the dielectric material is a polar dielectric material, then EM can be found. If we are going to consider non-polar dielectric material, then there is no permanent electric dipoles will be found. So EM will be 0. So for this case, here we consider this is a non-polar dielectric material. So hence EM value will be how much? 0. Because for this case, non-polar dielectric is considered. Okay. Hence equation number 1 will be how much? E local will be E naught plus EP plus ES. And we know that E naught plus EP, vectorially they are going to be, these both the electric field intensity is going to be subtract, but the resultant, if we are going to consider E naught plus EP, see here it is written that E naught plus EP, but actually this will be vectorially they are going to be subtract, will be how much? Will be E, that we know. So resultant electric field intensity by considering E naught and EP is your E plus ES. So hence we found the local electric field on this atom or molecule or the atom, individual atom or molecule inside the dielectric material is experienced by the net electric field, that is your E plus Es, for a non-polar dielectric material. If it will be polar, then Em another term will be considered, but in this case we consider a non-polar dielectric material. So now we are going to go for the evaluation of Es. Okay, so why we are going to evaluate this Es? Because here you can see that we know this value, E naught value, we know that is your sigma f by epsilon 0, and EP value is nothing but your sigma p by epsilon 0. So here E value already we know, E value equal to, this is your EF by epsilon naught minus EP by epsilon naught, that we know. These things already we have been evaluated in our last topics. These things we discussed in detail. Okay, so here to find out the local electric field, we have to evaluate only this Es. That means electric field due to charge on this spherical cavity. Okay, so electric field intensity due to this charged spherical cavity, Es, we have to evaluate, and then whenever we are going to add with E, we can found local electric field. Okay, now here you can see what is the base difference between this figure and this figure. Here you can see that this is the small surface ds we have been considered, and ds direction along this perpendicular to this surface, along this direction towards the center, and this side is charged by positive, this side is charged by negative on this cavity, whatever we have been discussed here in this slide. Here you can see on this side positive and on this side negative charge. Now we are going to discuss in detail to find out the value of Es. So here you can see that if this whole cavity is charged by positive charge on the left face and negative charge on the right face, then net electric field intensity will be along this direction, because if we know this is the positive charge and negative charge will be separated by a distance, so electric field intensity will be like this. So here this side is your positive, this side is your negative, so net electric field intensity will be along this direction. That means we can predict that Es direction will be along this direction. Okay, so here also I drawn this one itself in your figure 2. Now we have to find out the magnitude of Es. So this is one of the important topic of your syllabus. Always 90% chances is there that you are going to get this question in your exam, 90% chances. So watch carefully and write down your note. Okay, so to evaluate this magnitude of this Es, consider a small area ds on this cavity, on the surface of this cavity, this one. So if it is ds, let us q dash charge is on this ds surface, hence q dash value will be how much? P dot ds. These things already we have been discussed that for a curved surface, charge on a curved surface will be equal to how much? Polarization vector dot product with scalar product with surface vector. So this surface, if we are going to consider this is the ds, and this surface vector or area vector along this direction, this is the ds vector, this one. Okay, this one, and this one is your p vector. So angle between them is how much? Theta. So q dash, that means charge on this small surface ds will be how much? P dot ds. These things already we have been discussed in our topic number 3. I am going to show you here. In topic number 3 we have been discussed relation between your polarization vector and surface charge density. Here, this one, P dot A, charge on a surface is equal to P dot area vector. So hence the same thing, or the same expression we have been used, that charge on the ds surface, small ds surface, if it is q dash, then q dash value will be polarization vector scalar product with ds vector. So that will be P ds cos theta. Hence, electric field intensity at C due to Q dash charge will be how much? If this is the charge, then the electric field intensity ds due to this charge will be how much? 1 by 4 pi epsilon 0 Q dash by r square, because we consider that the radius of this sphere is r. So from here to this distance is your r. So hence electric field intensity, that is your DES, electric field intensity due to this charge on this surface at C will be equal to this much, 1 by 4 pi epsilon 0 q dash. So here q dash is found as P ds cos theta. We just substituted here. Okay. So but at C, DES has two components. Here you can see at C, see, this is your positive charge. So if this is the positive charge, the electric field intensity at C along this direction, it will be along this direction. Okay, this is the DES direction. And if this is theta angle, so obviously this angle will be theta. Okay, so if this is the theta, ds has two components. One is your ds sine theta and another is your ds cos theta, right? Same thing it has been written, but at C, ds has two components, ds cos theta and ds sin theta. Just refer the figure 1. Okay. Okay, but from figure it can be noticed that ds sin theta components on a elementary ring will be cancelled with each other. Most important point that you have to understand. I'm here explaining, you just carefully watch. Now you just consider just opposite surface area. Here this is your ds, another element ds you just consider at here, just opposite to this surface. This is also, you just consider this is also ds element. So due to this ds element, electric field intensity at C will be along this direction, will be along this direction. So if it is so, then as we consider that this surface area is just opposite to this one, so if this is theta, so obviously this angle will be theta. Okay, if this angle will be theta, so this angle also will be theta. So hence this ds has two components, one ds sin theta along positive y-axis direction this way, and another your ds cos theta along positive x-axis direction. Clearly I have been mentioned in the figure. So here we can found that ds sin theta component of this surface and ds sin theta component of this surface both are opposite with each other and equal magnitude. So both sin theta component will be cancelled with each other. Due to these two surface, the net electric field intensity is nothing but addition of these two components. Likewise, if we are going to consider a elementary ring, this one having the thickness ds, then all the ds components ds elements. Suppose I am going to consider here one element and just opposite another element here on the elemental ring. On the elemental ring, here one element, here one another element. So due to this element at C, two component we are going to find out. One along positive x-axis direction, use your cos theta component, and another will be along this, along y-axis, sin theta component along this negative y-axis direction. Due to this surface, which is exactly opposite to this surface, at C, electric field intensity also has two components. One will be along positive x-axis and another will be along positive y-axis. So considering these two surfaces, the cos theta component will be add up, whereas sin theta components are going to be cancelled with each other. So if we are going to consider the entire surface area of this ring and corresponding electric field intensity at point C, the net electric field intensity due to this elementary ring will be addition of cos theta component, and whereas your sin theta component is going to be cancelled. So if we are going to consider this elementary ring and its corresponding electric field intensity at, this is the elementary ring and its corresponding electric field intensity at C, then mathematically we are going to add all the cos theta components. Okay, same thing it has been written here, that ds components on the elementary ring will be cancelled with each other, where ds cos theta components is going to be add up. So same thing it has been written figure 1. From figure 1 it can be observed that the addition of all the ds cos theta components is equal to the electric field intensity at C due to elementary ring having radius r sin theta. Here you can see net electric field intensity at C or on this atom or molecule due to this elementary ring, is the addition of all the cos theta components. Okay, and radius of this elementary ring will be r sin theta. How? Here you can see this is the elementary ring. Okay, this is the theta and this length is your r. So obviously here you can see this is the radius of this elementary ring. So if we are going to consider this right angle triangle, this is the right angle, this is the right angle triangle. If this is the r distance and this is the theta, so obviously this is value will be how much? R sin theta. So the radius of this elementary ring is your r sin theta. Okay, and inscribed, and this ring is inscribed here, n I forgot to write, inscribed in between theta and d theta. Theta in between theta and d theta, this thickness or this ring is inscribed or enclosed. I'm going to write here inscribed en. Okay, okay, in between theta and d theta. Let us consider dr is electric field intensity at C due to the elementary ring. Right here in our previous slide, ds is the electric field intensity due to this small area. Now we are going to consider der, r for the ring. dr is the electric field intensity at C due to the elementary ring. Then what will the value? The value will be the addition of all the ds cos theta, that is your due to all the elementary areas electric field intensity at C, that cos theta component of all the elementary areas is going to be add up, and it will give the net or resultant electric field intensity of this entire ring. Okay, so der, which is represents the electric field intensity at C due to the elementary ring, will be des cos theta. Des value here we found this one 1 by 4 pi epsilon 0 p ds cos theta by r square. This much value we are going to be substitute over here, this one 1 by 4 pi epsilon 0 p ds cos theta by r square. Okay, okay, into another cos theta is there, cos theta. Now der will be equal to 1 by 4 pi epsilon 0 p cos square theta, here cos theta it will be cos square theta by r square into summation over ds. What is the meaning of this summation over ds? The summation over ds means is the total surface area of the elementary ring. Okay, so here you can see that des cos theta is the value of electric field intensity of a particular elementary area, this one. If this is your ds, then due to this es, what is the electric field intensity at here? Des cos theta, because sin theta component is going to be cancelled out. Okay, so here des value we found this much, just substituted, cos theta is there, so cos square theta we found, but into summation over des means we are going to consider all the ds on this elementary circle, so on this elementary circular strip or a ring. Okay, so for this particular ds, what is the electric field intensity at c is this one. If we are going to consider all the ds on this ring or elementary ring, then what will be the electric field intensity at c? Then I have to just add all the electric field intensity of each and every individual ds. Okay, so for one ds if this value, then for all we have to add it. So this ds is nothing but what? Total surface area of this ring. Simple. So this summation over ds is represents total surface area of the elementary ring. Now our work is to find out the total surface area of this elementary ring. Here you can see, we know that if this is a circle, then the circumference, that means total length of this circle, will be equal to 2 pi r if r is the radius. Okay, so for this circular strip, the circumference will be how much? 2 pi r is your r sin theta. This is your r sin theta, radius is your r sin theta. Okay, so 2 pi r is your total circumference of this elementary ring, and thickness into this thickness will be give us the total surface area of this elementary ring. So this much thickness is nothing but how much? R into d theta. Here you can see, this, here you can see this one is your r, this is your d theta. So what is the thickness? This one, if this is your thickness, this thickness will be r into d theta. Got it? See, like this, if this is d theta and this is your r, so what is this one? This one is your r theta, we know, r into d theta. So this, the thickness of this elementary ring is your r d theta, and the circumference is your 2 pi r sin theta. So whole surface area of the elementary ring is your 2 pi r sin theta d theta. So summation over ds is nothing but this one, we have to just substitute over here. So der will be equal to 1 by 4 pi epsilon 0 p into cos square theta by r square, as such it has been written, into 2 pi r sin theta into r d theta will be equal to 1 by 2 epsilon 0 p cos square theta sin theta d theta. Now resultant electric field intensity es suppose ES, what we intend to find out at C is due to whole sphere. See here, this value is the net electric field intensity due to this elementary circular strip, but we want to find out the resultant electric field intensity at C due to this whole sphere, that is your ES we want to find out. So for the whole sphere, what we have to do? So same thing, it has been written that the resultant electric field intensity ES at C due to the whole sphere or whole spherical cavity, whole sphere or whole cavity, you can write, will be how much? That is your addition or integration of electric field intensities of all possible elemental rings to cover the whole sphere. So this is one sphere. So all possible rings, if we are going to consider, see, on the surface one ring, another ring, this will be 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 another ring. Okay, like this. Then this will be another ring. If we are going to consider like this to cover whole sphere, here we have been started. Okay, then for this elementary ring, what will the angle? Angle will be 0. For this elementary ring at this end, what will the angle? See, from here, from this ring we have been started, this theta is your 0 degree. Now whenever we are going to move larger and larger radius like this, then this angle is moved like this, 0 to pi by 2, then pi. So if this angle will be moved from theta to pi, then we are going to cover all the area of this sphere. Okay, so addition or integration of electric field intensities of all the possible elementary rings to cover the whole sphere, that means integration of this DER from 0 to pi. So ES is nothing but your resultant electric field intensity at C due to whole sphere will be 0 to pi 1. So here we have to just put DER value this much, 1 by 2 epsilon 0 p cos square theta sin theta d theta. So next mathematical work is this one. So this much we found. To integrate, here we put x equal to cos theta, dx equal to minus sin theta d theta, sin theta d theta will be minus dx. So considering the limit, if we are going to put theta equal to 0 degree, see here I considered x equal to cos theta, so only for that we have to also change the limit. So for theta equal to 0 degree, lower limit is 0, so x will be how much? Cos 0 will be 1. So theta, for theta equal to pi, higher limit, cos theta will be minus 1, so limit will be changed from 1 to minus 1. So es, this one will be equal to 1 by 2 epsilon 0 p, integration limit from 1 to minus 1. This one cos theta considered as x, so it will be x square, and sin theta d theta is nothing but minus dx. Okay, simple. So es will be 1 by 2 epsilon 0 p minus 1 to 1 x square dx. Just integrate it, it will be x cube by 3, and limit is minus 1 to 1. So you just put the limit and you can found that es equal to p by 3 epsilon 0. So here p is nothing but polarization vector magnitude, that is your polarization per unit volume or dipole moment per unit volume. This is most important, you have to remember. This is the dipole moments, induced dipole moments per unit volume inside the dielectric material by 3 epsilon 0. But we know that E local equal to E plus ES, this one. Okay, E local, we have to find out E plus ES for a particular atom or molecule inside the dielectric material. So therefore E local will be E plus this value P by 3 epsilon 0. So in vector form it can be written as E local equal to E plus P by 3 epsilon 0. See, for this E value, some books it has been written that sigma, because E is nothing but E naught minus EP. No, so E value equal to E epsilon F sigma F by epsilon naught, minus sigma uh, p by epsilon naught. This much also you can substitute over here. These things already we found, but here no need. The in the magnitudically E local will be this one, and in vector form this will be the answer. Okay. So if this question asked in your exam for 6 mark, you have to start from here. You have to draw this figure. So see, this figure no need to draw this one. You have to draw this one figure directly. This one is your figure 1 and this one is your figure 2. This figure is required to find out the r sin theta value, and all the things whatever I written, this one, these all the lines you have to write, and these all the lines you have to write. Not much more than that you have to write for the 6 mark question. Okay, this much is enough, because uh, what I prepared the note focusing to your exam. Okay, focusing for the 6 to 7 mark question. So you should not be bothered about the note. You can consider this is your exam note itself. Okay, so we found E local equal to this much. Now we are going to move our next topic, that is your Clausius-Mossotti equation. This is also one of the important question uh, asking in your exam. Okay, so let's start this topic number 10, that is your Clausius-Mossotti equation.